Review our discussion of defects. When we talk about defects, we can talk about defects in crystals and defects in amorphous materials. In amorphous materials, it's a little more challenging because we're basically looking at this large network structure and we don't have a long-range periodicity. So we're not talking about those most of the time. Most of the time we're talking about defects in crystalline materials, and we classify those defects according to their dimensionality. So a zero-dimensional defect is considered a point defect. It's any type of defect which occurs and it happens at a 1 or 2 atom site distance. A one-dimensional defect is called a line defect. We talked about dislocations in class and we'll review those in a later video. Two-dimensional defects are surfaces. They can either be the surface of the material. We talk about crystals in terms of them being infinite in size, but at the same time, surfaces are sometimes very important, especially when you start getting to smaller structures. For example, you start talking about nanostructures that are being used. Surfaces become important. And we can think of those as a class of defect. And lastly, we have 3D defects, or bulk defects. And you can think of those as almost as point defects that are larger. For example, if you have a void in a material, that void, it contains lots and lots of vacancies. And a vacancy would be a point defect that's at the atomic scale, and a void would be a macro scale bulk defect. So let's talk about point defects. If we talk about these point defects, we should talk about whether they're called a defect or a dopant. If it's detrimental and you don't want them, then we call them defects. If you put them there on purpose, then we call them a dopant. So for example, when we create a semiconducting material, we have silicon, and we will put boron and phosphorus in as dopants in order to control the electronic properties. In contrast, for example, you might have copper or gold in your silicon, and those completely damage the electronic properties, so we would call gold point defects in silicon a defect instead of a dopant. These defects are classified into whether they are intrinsic or extrinsic defects. An intrinsic defect is a defect that does not have some type of outward contaminant. So it's just a defect that's just intrinsic to the composition. And those can be vacancies, so a missing site. They can be self-interstitials or self-substitution. In contrast, an extrinsic defect has to have an external contaminant that's added or external dopant that's added, and those can either be interstitial or substitutional. This is an example of what we were talking about. So imagine we have some crystal. This is a two-dimensional crystal, and our two-dimensional crystal goes off in infinite directions. And I drew it as having a basically a little rectangular set of unicells, and in the unicells I put a blue and a red atom. So a vacancy would be a case where you're missing an atom, and I represented that as a little dashed hole. So that's an intrinsic defect. Then talking about self-interstitials and substitutions, well, a self-substitution is when an atom is sitting on the wrong site. So for example, we have red atoms and blue atoms. So for example, right here, I create a situation in which a blue atom is sitting where a red atom should. So that's a form of self-substitution. And of course, if your composition is just a single element, for example, just gold or just lead or what have you, you cannot have self-substitution. You have to have at least 2 elements in your compound for there to be that. And then we have interstitials. And interstitials have to do with sites that exist between the standard sites in your unicell. So for example, your unicell is this rectangle with a blue and a red atom. Well, then it's possible that atoms will sit in between those sites. For example, perhaps in our lattice, we have interstitial sites that are sitting between the red and the blue atoms. And those would be the interstitial site, and those can be occupied, for example, by a red atom or a blue atom, and that would be a self-interstitial. Now, in contrast, we can talk about extrinsic defects, and in that case, we have something, for example, a interstitial. So I put this orange atom that is some contaminant and is sitting at the interstitial site, or it can sit substitutionally. For example, here's an orange atom that's sitting on a blue atom site. Now, it's worth commenting on that anytime you have a point defect, whether it's interstitial or substitutional, it requires energy to create that. And in part, that has to do with the fact that we, for example, here, we had to take a red atom out and put a blue atom in. And those are different atoms. They have slightly different sizes. They have slightly different bonding properties. So whereas before I had this nice crystal with blue atoms being bonded to red atoms, being bonded to blue, being bonded to red, now what we've created is a red atom bonded to a blue, which then bonded to a blue atom. And that difference in the bonding requires some additional energy to be added to the system. These defects will also sometimes interact with each other. For example, where we have a vacancy, well, that vacancy means that all the atoms nearby are going to squeeze in, right? You've got a little void. And as a result, it's not uncommon for interstitials or perhaps substitutional species, which are too large, to be attracted. So we can talk about the elastic compression or tension associated with having atoms that are missing, atoms that are too small for the lattice site, or atoms that are too big for the lattice site. And these atoms will move around in order to minimize the elastic energy.